Now it's time that we take a look at the dot product of two vectors. The dot product is also known as the scalar product or the scalar multiplication of two vectors. Till now we have talked about what happens when you multiply a vector by a scalar, but now we will talk about multiplying two vectors together. Okay? You cannot divide two vectors. You cannot have a situation where you say divide vector A by vector B. This is not possible. And as if to compensate for this loss of operation, there are two types of multiplication that are defined for vectors. One is the scalar multiplication of vectors, the dot product, and another multiplication of vectors is known as the cross product. That is known as the vector multiplication of vectors. Okay, so the vector multiplication of vector produces a vector, and the scalar multiplication of vectors, of course, produces a scalar, right? So let us say that there is a vector A and there is another vector B. The dot product is represented by using this dot symbol between A and B, and this is equal to the magnitude of A times the magnitude of B times the cosine of the angle between the vectors A and B. Okay, so let us say that you have a vector. Let us say force vector is 3 Newton along this direction, and let us say the displacement vector is, okay, I should use the arrows. The displacement vector is 2 meters along this direction, and the angle between the two vectors is, let us say, 45 degrees. So the F vector dot S vector will be written as 3 Newton times 2 meters times the angle between the two vectors, which is cosine of 45 degree. So it is equal to 6 by root 2. And Newton meters, of course, the units must not be forgotten. So 6 by root 2, if you rationalize it, then it comes to 3 root 2 Newton meter. Now later on I will tell you that F dot S is nothing but the work done by the force, and 3 root 2 Newton meter can also be written as 3 root 2 joules, but that is something that we reserve for a future chapter on work, power and energy. So I think you have understood that how to take the dot product of two vectors is that simple, except you need to look out for this very special case. Let us say that the force F is 3 newtons like that, and the displacement vector would have been given to you like this, 2 meters in this direction, and this angle then is 135 degree. You can see this is an obtuse angle, right? I hope that by our discussion on angle between two vectors, you are not going to take this angle as the angle between the two vectors. You know that you have to extend this line along the S vector and then take the acute angle between the two vectors, and that will serve as the angle between the two vectors as we have used. Okay, so that is a case that you need to look out for. So I will write look out in red. Okay, so it is really that simple. Apart from that, there is another representation of dot product that includes the 3 standard Cartesian coordinate unit vectors. Okay, so let us say that the vector A has been given to you like so. Let us say that the vector A has been given to you as some AX I cap, AY J cap, and AZ K cap. And let us say that the arrows, yes, the arrows. The vector B has been given something like BX I cap plus BY J cap plus BZ K cap. So again, the dot product is defined as AX times BX, the X components, plus the AY times BY, the Y components, and the AZ times BZ times Z, that is the Z components. Okay. Now there is a way in which you can arrive at this result. You can simply take the dot product between these two vectors, AX I cap, AY J cap plus AZ K cap. This is a vector, the A vector dot BX I cap plus BY J cap plus BZ K cap. Okay, so you take the first term and you take the dot product of that with the first term. You take the first term and you take the dot product of that with the second term, and you keep on doing so. But this first term is going to be AX, magnitude of the first vector, times the magnitude of the second vector, the angle between the two vectors. Now both these vectors are along the I cap direction, that is both these vectors are along the X direction. Okay, that is the reason why the angle between them is 0. So if this is the X direction, then A vector, then AX vector is something like this, AX I cap and the bx vector is also somewhere like this, the bx vector. So the angle between the two vectors is 0. Both of them are towards the x direction. So the cosine of the angle between them is going to be 1 because cosine of 0 is 1. So this is simply going to reduce to ax bx plus ax times by, j cap. You say the magnitude of the first vector, the magnitude of the second vector times the cosine of the angle between them. Ax is along the x direction and by is along the y direction. The angle between them is 90 degrees. So cosine of 90 degrees is going to be 0. So this whole term is going to be reduced to 0. Now that is something interesting, because whenever the two vectors are not, the two unit vectors are not the same, the terms are going to go to 0. Okay. As a result, all the I dot j terms, j dot I terms, I dot k terms, k dot I terms, j dot k terms, and k dot j terms, all of these terms are going to 0. The only terms that remain are the I dot I terms, the j dot j terms, and the k dot k term. And therefore you can see only 3 terms in the dot product, and all these extra terms, there are going to be 3 times 3, I guess 27, 9 terms that should be here. And out of those 9 terms, only 3 terms persist. The other 6 terms are all equal to 0. Okay. So that was another example. So let us say the force vector was given as minus I cap plus 3 j cap plus 5 k cap Newton, and the displacement vector is given as 2 I cap plus j cap plus 10 k cap Newtons meters. Then the work done vector, or no, sorry, the work done is a scalar, because the dot product between two vectors always is a scalar. Therefore the work done, which is the dot product between the two vectors f and s, is going to be a scalar. However, so f dot s, for the work done, just another term for f dot s, is going to be minus I cap plus 3 j cap plus 5 k cap dot 2 I cap plus j cap plus 10 k cap. Okay, and you can simply use this formula. Minus 1 times 2 is minus 2, plus 3 times 1 is 3, plus 5 times 10 is 50. So 53 minus 2 is going to be 51. And if you are particular about units, you can write Newton meter. And if you have some knowledge about joules from previous classes, then you can also write this as joules. Okay. So for now we are going to leave it at Newton meters, and we're also going to remove this W from here. So that is pretty much how you take the dot product between two vectors. You can see that this is a scalar. You don't have any direction over here. Okay, you don't have any unit vectors to specify the direction. You don't have to specify the direction in any case. So the dot product is therefore known as a scalar product, again because it outputs a scalar. Final word about the dot products is that the dot product is commutative. Okay, the dot product is commutative, so whether you take A dot B, it is the same as B dot A. When we go on to cross products, we will find out that the cross product is not commutative, simply because of the direction that is attached to the cross product. We are going to talk about the cross products in detail in the next video. So if we are talking about commutative property, then dot product is definitely commutative. You can also check from here that f dot s was like this. So if I did s dot f, then I would have simply written 2i cap plus j cap plus 10k cap, and then I would have dotted it with minus I cap plus 3j cap plus 5k cap, and then I could have simply said that 2 times minus 1 is again minus 2, 1 times 3 is again 3, and 10 times 5 is again 50, and again this is 51 Newton meters. The answer is same. And again, if in this even if in this example where we are using this particular formula, that it is AB cos theta, if I would have written it is s dot f, then I would have done 2 meters times f would have been 3 Newton, and the cosine would have been minus 45 degree. Since we are going from s to f, you can say that the cosine is minus 45 degree, because here I have defined the cosine from f to s. Okay, traditionally the angles in trigonometry are defined from the bottom towards the top. Now that's a very vague word that I have used, bottom towards the top. So when you learn trigonometry, you will find out that if this is the Cartesian plane, you take this as 0, and as you keep on progressing towards this anti-clockwise direction, you increase the angles. But for now, we can say that I have used the opposite sense, that the way we go in clockwise direction, the angle is increasing. Okay, just for this problem. Then S dot F is going to be minus 45 degree, because from F dot S we have a clockwise increase, therefore we take plus 45 degree. Therefore for S dot F we take an anti-clockwise path, therefore we are using minus 45 degree over here, and this is going to be 6 times. Now cosine of negative angle is equal to the cosine of that angle. This is equal to 6 times cosine 45 degree. This is a standard trigonometric relation, that cosine of minus theta is the same as cosine of theta, and this is equal to again 6 by root 2 or 3 root 2 Newton meters. Okay, so whether you take S dot F, whether you take F dot S, whether you take A dot B, whether you take B dot A, they are the same thing. And dot product is commutative. It's a very important property, and this is what sets it apart from the vector product, as we are going to see in the next video. Thank you.